Hi everybody, a very good morning. Okay, I have to be made host. I'm not made host yet. Just a moment. Okay, I made the host. Let me share the screen. So last class we have successfully completed your aldehydes, ketones, carboxylic acids, right? And I think someone asked me that we can start with coordination compounds, right? So that we'll do now. Right, we'll start with coordination compounds today. All right. Something is not. Okay, so people, this chapter is again going to be a very interesting chapter, right? As the name tells you, we are going to study about a special class of compounds called as coordination compounds, which you might have encountered in some of the chapters. You might have come across, but you don't know that those are called as coordination compounds. Okay, right. So people, so these coordination compounds are very special, okay, because they are extensively used in medicines. Okay, they're extensively used in some laboratory techniques. Okay, and also, like, if you remember, there is something called a cisplatin. Okay, there is something called a cisplatin. This cisplatin is actually used in the cancer therapy, right? Used in cancer treatment. This is nothing but a coordination compound. Okay, right. So what exactly are these coordination compounds? Okay, so what you have to understand is, from the name, what you understand is there is this coordination, right? Basically, all these compounds are going to have only coordinate bonds. At least most of the bonds in the compounds, in these kind of compounds, are going to be coordinate bonds, right? We have to understand first what are coordinate bonds, right? See, in a normal covalent bond, what happens? Say I have A, B, I have one electron coming from this, another electron coming from this. Those are shared, and you have a normal covalent bond, right? Okay, but in the case of coordinate bond, what is going to happen is there is going to be one species which is going to donate both the electrons to the one of the atom. That means it is not mutual sharing. Okay, it is not mutual sharing, whereas in the case of normal covalent bond, you have mutual sharing. What do you mean mutual sharing? One electron comes from one species, another electron comes from one another species, and you'll mutually share between A and B, right? But in this case, you understand that there are going to be two electrons coming from one of the species only, right? And that is going to be donated to this A, and that is going to get shared, right? So that is why we represent the coordinate bond like this. Now, whenever I put an arrow mark, that arrow mark represents from where to where, which atom is donating, right? To which atom it is getting donated, right? That is the arrow mark we should put, right? So in all these compounds, we are going to have only these kind of bonds, coordinate bonds. Okay, right. And like, if at all you want to understand coordination compounds, right? Actually, people thought differently in the earlier stages, like whenever these was introduced in, say, in the 1700s, 1800s, right? Or say that there was confusion between this there were confusions between this double salts, right, and coordination compounds. Okay, now what are the examples of double salts? Say, for example, there is a salt like this, right? There is this salt called as carnallite. Okay, so carnallite was basically K2SO4. dot MgSO4 dot some 10H2O, something like this, right? So this is what is called as Carnallite. Okay, right. So you understand that what in double salts there is going to be more than one cation, right? More than one cation is going to be present. Understand here, obviously from here we can write, we can say that your pattern here is going to be K plus, and here it is going to be Mg2 plus, is it not? So you understand that there is going to be more than one cation, but only one anion is there, that is SO4 2 minus, only one anion is there, right? Now people, how do we differentiate between, so like you can write a coordination compound also like this. Say I can write NiCl 3 times dot 3H2O, something like this also will be able to write. Okay, so this and this looks very similar, isn't it? Right, this and looks very similar, right? Except for the fact that here I have only one cation, but this is actually going to be a coordination compound, right? This is actually going to be a coordination compound, right? So there are a lot of confusions between this particular, double salts and the coordination compounds initially, right? Now, how people understood, right? How did people understand what exactly is the difference between these double salts and coordination compounds? Okay, right. So what you can do is, if I dissolve, for example, Carnallite in water, okay, if I dissolve, say in any double salt for that matter, for example, Carnallite in water, I'm going to dissolve. Okay, right. So what they observed is they got K plus ions, right? They got Mg2 plus ions, and they got SO4 2 minus ions. Okay, right? They got K plus ions, Mg2 plus ions, and SO4 2 minus ions. Obviously, that those are ions present here. You can easily understand that, right? But if any coordination compound is dissolved in water, right? Now, what do we expect? We expect that, say, for example, some Ni2 plus ion can be formed, Cl minus ion can be formed. That is what we expect, right? But this was not happening, right? This was not happening at all, right? Rather, they were actually getting some other species like this, NiCl3H2O, say NiCl2H2O, some minus here, and sorry, plus here, and Cl minus, something like this. Okay, so these kind of species were what they are seeing, not Ni2 plus and Cl minus, and that is what we generally expect, isn't it? So what we have to understand is the ionization itself is going to be different. How this particular molecule undergoes ionization, right? So coordination compounds does not give all the ions which you see in the particular molecular formula, right? They are going to have some kind of this brackets which we put, and all that kind of species. That ion is only getting formed, which is nowhere related to this double salts. Okay, right? So that is the first conclusion we make, right? So whenever we take a molecular formula of a coordination compound and we dissolve it in water, right? And we dissolve it in water, what we have to understand is you are not going to get all the characteristic ion. Rather, you are going to get some other weird species like this, right? We are going to get something like this. All right. Okay, so if that's the case, you have to investigate more, right? We have to investigate more and see what exactly is happening here. Okay, so people, so a coordination compound, right? A coordination compound contains two parts, right? It consists of two parts. One is the coordination sphere, we call it, right? One is the coordination sphere part, and another one is your counter ion part. Okay, so any coordination compound will contain two things. One is the coordination sphere part, the other one is your counter ion part, right? So this coordination sphere part, in the coordination sphere part, we will be representing it within your square brackets. Okay, we will be representing this within your square brackets. Okay, and this counter ion is going to be outside, right? Whatever is outside this place, we will be writing some ion, right? So in this case, you understand that, for example, this one is your counter ion, and this one is your coordination sphere, right? So whatever is inside the bracket, we are going to call that as coordination sphere, and whatever is outside the bracket, we are going to call it as counter ion. Okay, and whatever is there inside the coordination sphere will not ionize. Right? That means whatever, if at all you have Mg2 plus something here, right? You will understand that that is not going to get ionized. If they ionize, they will ionize as coordination sphere and the counter ion separately. That is how they will ionize. Okay, right. So only thing you have to understand is whatever is inside the square brackets, that particular thing is what is called as your coordination sphere. Whatever is outside the square bracket is what is called as your counter ion. Right. I hope that makes a lot of sense. Right. Okay. Now delving deep into this coordination sphere. Right. Dwelling deep into this coordination sphere. Right. What and all is going to be there in the coordination sphere? Okay, now let us write a general formula, right? Say I have some metal, okay, and I'm going to have some L, I'll write, and some N, some number of L are there, right? And I'm going to have some positive or negative charge, right? We can write A plus or minus by L. Right. Okay. So this is how a general coordination sphere looks like. Okay. Right. Now we have to understand what are the parts of this coordination sphere. Okay. Now this A plus or minus, it can be plus or minus, some value of positive charge or some value of negative charge, depending on what is the coordination sphere. Okay. Right. So this is what is called as the charge of the coordination sphere. Coordination sphere. Right, and this M which we write is what is called as your central metal ion or central metal atom or ion. Okay, and this L which you write, that those are going to be negative charges. We'll speak more about this, right? And these are what are called as ligands, we call it. Okay, right. So these are all the parts of a coordination sphere. Right, so we have something inside the square bracket, that is what is called as coordination sphere. Right, inside that there'll be a metal, right, and that metal is what is called as central metal ion or central metal atom. Right, and obviously other than the metal you are going to have some negative charges or some neutral species you are going to have. We'll speak about it in depth, don't worry. And these are what are called as ligands. Right, and obviously we can have this A plus or minus, that is going to be the charge of the coordination sphere. Okay, right. Now, depending on the charge of the coordination sphere, you will be actually able to, classify them into three types, right? One is what is called, can be a positively charged coordination sphere or a negatively charged coordination sphere or say a neutral coordination sphere. I think from the name itself, we can understand, right? Right. We can have either a negative charge or a positive charge, or it can be having zero charge on the coordination sphere. Depending on that, I'll be able to classify it. Okay, say if at all I have to give you some example, right? Say if I can write Cu H2O, right, for positive, I'm telling Cu H2O 6 times 2 plus, right? Now what I understanding, copper is your metal, H2O is your ligand, right? And this particular 2 plus indicates that it is positively charged. Right, say I can have a negatively charged species. Say for example, I can have CO Cl 6 times 3 minus. Okay, now what I say again, cobalt. CO is cobalt, right? So cobalt is going to have a the central metal atom. Chloride is your ligand, and this 3 minus indicates that it is going to be a negative charge, right? And say neutral species. Now say I can have NiCO 4 times. Okay, now what are you seeing? You are seeing that there is no charge here, zero. The charge is zero. Okay, so depending on what is the charge on the coordination sphere, you will be able to classify them as positively charged coordination compounds. Second, negatively charged coordination compounds or neutral coordination compounds. Okay, right? Fine. So that these are the things. These are the basic things. This is the overall picture of how a coordination compound looks like. Right, so obviously if at all you have a 2 plus here, I need to have something which is going to have a charge of 2 minus, and if at all you have a 3 plus, I need to have something outside to have a charge of 3 plus. But in this case there need not be any counter ion as well, is it not? Because already the charge is 0, right? And obviously we don't have anything to counter it, right? But depending on what is the charge on the coordination sphere, outside the counter ion should possess the oppositely charged, that same magnitude but opposite charge you should have. Right, I hope that makes sense to you. That makes sense to you. All right. Okay, so we talked about the coordination sphere. We talked about what is counter ion, what are the charges on the coordination sphere and stuff. Right. Now we'll move on. We'll move on to speak about the ligands. right? What do you mean by ligands and what are the different types? Okay, so people, ligands. Okay, so when I told you that all these coordination compounds are going to be made out of only these coordinate bonds, is it not? Right? All the coordination compounds are actually going to be made out of only coordinate bonds, isn't it? So in the coordinate bond, you understand that there was an electron donor, right? There was an electron donor, and this A was acting as an electron acceptor. Is it not? Right? There was an electron donor, that is whatever is donating the 2 electrons, that is an electron donor, and there was one electron acceptor. Isn't it? Right? So these ligands are the ones which are going to act as electron donors. Right? Say for example, we have a metal. Obviously, metals will have positive. They will not have much electrons present in them. Right? But a ligand comes. A ligand comes, which that is why we write L. L is your ligand. Right? That L is your ligand, and these 2 electrons are going to be donated to your metal atom. Right? So whichever species is able to donate electron to the metal, that particular species inside the coordination sphere is what is called as your ligands. Okay, right? Fine. Now, these ligands again can be classified into so many types. Okay, right? Say based on the charge, sometimes you'll be able to this thing, right? Say ligand. I'm going for classification of ligands. Right? What are the different types of ligands we can have? I'm going to see, but there are various bases, like various parameters we can use for the classification of ligands. Right? Okay. So classification of ligands. Right? Say first one with respect to charge, we can see. Okay. Say under this, we can have again positive ligands, right? We can have negatively charged ligands, or we can have neutral ligands. Okay. Right? Positively charged ligands, neutral ligands, or negatively charged ligands we can have. Right? Say what and all can be examples. You can have, say, for example, if at all you want a positively charged ligand, all that you have to understand is the ligand, this particular L, is now going to have some kind of positive charge. Okay, right? Then you can ask me, sir, it is positively charged, but still it is able to donate electron? Yes, why not? Right? See, having charge, having positive or negative charge is not going to be the criteria for a donate. All it needs to have, all a ligand needs to have is at least one lone pair of electrons. Is it not? All the only criteria for something to act as a ligand is that it should have a lone pair of electron, and that lone pair should be able to be donated. Right? That lone pair should be donated to another species. That capability should be there. First criteria is lone pair should be there. Second criteria, that lone pair, having the lone pair is not sufficient. We should be able to donate the lone pair to some other species. Right? Those 2 criteria are satisfied. It doesn't matter what charge that particular ligand has. Right? Say for example, if you take NO plus, right? This is your NO plus. This is what is called as nitronium ion. Positive charge. Right? Now you can ask me, how is it that it is able to donate electron? Now, if you look at the this thing of NO plus, right? You will understand that oxygen is indeed having a lone pair, and you can also have nitrogen to have a lone pair. Right? You can have oxygen to have a lone pair or nitrogen to have a lone pair. Right? So at the end of the day, what are you seeing? The lone pair is there, and they will be able to donate to some other species, either oxygen or nitrogen. Depends. That depends on the compound. Okay, so the both nitrogen and oxygen is indeed having a lone pair, and that can be donated to the metal atom. Yes. Okay. Right. And negative charge is very easy to understand. So many negatively charged ligand we have, say Cn minus, Cl minus, Br minus, OH minus, anything, whichever you saw as nucleophiles. Right. All these things can come as negatively charged ligands. Right. Okay, right. Next, you can have so many other things also, right? We can see so many other things, but don't worry, we will see slowly what we have to do, right? All that you have to understand is these are going to have some kind of lone pairs on them, right? All of them are going to have some lone pairs on them, and that is going to get donated to the central metal atom, right? Okay, next one, neutral ones, right? Say the one of the classic examples of neutral ligand is H2O. Right? How we understand this? Obviously, water is having, the oxygen atom on the water is actually having a lone pair. that can be donated, right? Another case, ammonia, right? Again, is a very good example that is having a lone pair that can be donated, right? And say I can have carbon monoxide. This is not cobalt. Please understand, cobalt we write like this: C, capital C and small o. That is cobalt, right? If I write capital C and capital O, that is carbon monoxide. Please don't confuse yourself. Okay, so again, you will understand that is actually that carbon is actually having a lone pair, and that can be donated, right? So any other example, you can have any amines. Amines also say RNH2, right? You might have studied about amines in your school. Again, that is going to have a lone pair, right? So that's what I'm telling. All that we require is lone pair on the ligand, and that should be that should be able to be donated. That is all that you have to understand, right? Charge, yes, positive charge, negative charge, and neutral ligands we can have, right? Okay. Any questions till now? Anybody has? Okay. I hope you guys are following, right? Okay. So that is with the classification of ligand with respect to their charge, what charge they have, positive, negative, and neutral, right? Now, second classification, we can move on, right? So second classification, I can have classification of ligands with respect to its denticity. Okay, with respect to its denticity. Okay, obviously, first you have to understand what do you mean by denticity of a ligand, right? Denticity of a ligand is nothing but the number of donor atom sites, number of donor atom sites in the ligand, number of donor atom sites in the ligand, right? What do you mean by this, people? Now look at this, right? Say I take hydrazine, for example. We saw hydrazine in your this thing, aldehydes, ketones, carboxylic acid. If you remember, where can you really tell me where exactly we saw hydrazine in your aldehydes, ketones, carboxylic acids? Quickly, where did we see this, people? Hydrazine formula. Yes, go on. Where did you see this hydrazine in your aldehydes, ketones, carboxylic acids? We saw this, right? Where did this come? Sorry.
Preparation of aldehydes.
Preparation of aldehydes? No, we didn't see it there.
Sir, Wolff-Kishner.
Okay. In Wolff-Kishner, we saw. Okay, that is good. Fine, Wolff-Kishner. Okay, what happened?
Sir, I think in even in biomolecules we saw the 2,4 DNP test.
Okay, that is hydrazine. Yes, I understand. Basically, yes. So hydrazine's formula is NH2, NH2. Is it not? That is the formula, right? NH2, NH2, right? Okay. Now, what do you understand? Let me write this properly. Okay, let me write it as NH2, NH2. Okay, right. What are you seeing here? You are seeing that this nitrogen is having a lone pair, and this nitrogen is also having a lone pair. Is it not? So now, say for example, I have a metal, right? I have a metal, right? And you understand that this nitrogen and obviously another nitrogen is there. Both of them are having a lone pair. Obviously, 2 hydrogen atoms. Don't worry about it. Right? Both of these can be donated to the metal atom. Right? Both of these can be donated to the metal atom. But say, for example, you have say H2 as a ligand. Right? So you have a metal and you have H2O as the ligand. Right? Now, obviously, you have only one donor site, only oxygen atom is there, and that is only having the lone pair, and this can donate only from one site. This has only one site, right? But this molecule has 2 sites of donation. Is it not? Because one nitrogen atom, second nitrogen atom, both of them are having a lone pair. Right? Say there can be another case. There can be another case like this. Say you take some, there is a ligand called as EDTA. Okay, it is called ethylene diamine tetra acetate. Okay, ethylene diamine tetra acetate, right? Once again, so we have CH2 CH2. I think it is CH, not CH2. Right? And we have, say, this one NH2 is there, one NH2 is there, and we have one COO minus and another COO minus. Oh, Tetra acetate. Okay, means we don't have, okay, we need to have two then. Okay, this hydrogen is also not there. Okay, let me write this from first. No problem. Right. So we have carbon, and that is having two NH2s. Right. And we have one COO minus like this, another COO minus like this, COO minus like this, and COO minus like this. Okay, 1, 2, 3, 4. Okay, right. So this ligand is what is called as your EDTA, right? Ethylene diamine tetraacetate. Okay, now if you look at this, how many donor atom sites we can have if you check, right? Say this nitrogen is having a lone pair, this nitrogen is having a lone pair, so this is donor site number 1. Yeah, exactly. It is going to have 6 donor sites, is it not? And obviously this oxygen is going to have a lone pair. Third one, this oxygen also has a lone pair. Fourth one, this oxygen atom has a lone pair. Fifth one, and this oxygen atom also has a lone pair. Again, another donor site. Okay, so what are you seeing? The same molecule will be able to make 6 coordination bonds with your central metal ion or central metal atom, right? So this particular number of donor sites, right? The number of donor sites, that is what is called as your denticity of the ligand. How many sites from which you will be able to donate electron to the metal atom, that is what is called as your donor site. Right, so you can have only 1 donor site, 2 donor sites, 3 donor sites, 4 donor sites, 5, 6, maximum I think is 6. Okay, so maximum of 6, minimum of 1 donor site you can have. Right, so based on that, you can have, let me write this down, right? Based on that, you can have, say, something called as monodentate, okay, I hope the spelling is correct. Okay, monodentate ligand, they will have only single donor site. Right, say for example, Cn minus, Cn minus is going to have only 1 donor site, H2O is going to have only 1 donor site, anything which has only 1 donor site. Cl minus is also going to have only 1 donor site, right? So all these are monodentate ligands. They have only single donor site from which they'll be able to donate electrons, right? Say you can have didentate, right? You can also call it as bidentate. Some books call it as bidentate, some books call it as didentate. Both are correct. Obviously, what you have to understand is here I'm going to have 2 donor sites. Right? We are going to have 2 donor sites. Right? Say ethylene diamine is one very good example. Right? Ethylene diamine. Right? Ethylene diamine means you are going to have CH2, NH2 like this, CH2, NH2 like this. Okay, now what are you seeing? You have one lone pair here, another lone pair here, donor atom 1, donor atom 2. So this is an example for a bidentate ligand. Right? Okay, now we can have tridentate also. Right? Say tridentate, you can have any kind of molecule. Say you have NH2 like this, CH, NH2, right? CH2, NH2, something like this. Right? Again, you have 1, 2, 3. 3 donor sites you have, right? So like that you can have tetradentate, pentadentate, hexadentate, and I can just give you the example for hexadentate. Hexadentate, just now we saw hexadentate example is EDTA, right? You know what is the structure also. I gave you the structure of EDTA here, right? So again, that is going to have 6 donor sites. Okay, right. Fine. So that is the classification of ligands based on its denticity. And we understood what do you mean by density? It is the number of donor atom sites from which the electron pair can be donated to the metal atom. Okay, right. So these are all the classification of ligands. Now the question is, say I have some 6 donor sites, or say 5 donor sites, or 4 donor sites, whatever be the number of whatever be the denticity. Now instead of talking donor sites, we can talk in terms of the technical term. Say irrespective of whatever be the denticity, right? Irrespective of whatever be the denticity, it is not necessary for the ligand to use all its donor sites. Okay, again, I repeat, right? Even though we have more than one denticity, say the bidentate, tridentate, tetradentate, all these things we have, right? It is not necessary, right? It is not necessary for the ligand to use all its donor sites, depending on the requirement, right? Depending on the requirement, say out of the 6 donor sites, only 2 are required, then the ligand will be capable of donating only from the 2 donor sites, right? Say out of the 5 donor sites, only 1 is required, then only 1 donor site will be taken into the picture. Okay, right? But the when we classify this, we tell maximum, okay, this many sites are there. Okay, this many sites are there which are available for donation, right? That we can say. Okay, right. Now, these kind of molecules, some molecules like this, mostly when you have this bidentate, tridentate, tetradentate, and all those stuff, they will be they'll be able to act as flexidentate ligands. Flexidentate ligands, right? What do you mean by flexidentate ligands? Ligands are able, which will be able to say modify or change their denticities, modify or change their denticities, change their denticities, not densities, denticities. Right, that is what I was trying to tell you, right? Even though we have say 6 donor sites, 5 donor sites, out of them maybe only 1 or 2 would be required. The other 3 things will not be required at all, right? Say you can take, for example, say ethylene diamine itself. Say I had this NH2, CH2, CH2, NH2, right? So even though I have 2 donor sites, say assume that only this is involved in this thing and this is not involved in the donation part. Right, so obviously what you understand, even though it is a didentate ligand, only one of the site is involved in the donation part. Maybe I can just write a proper example also. I can write N H H CH2 CH2 NH2. Right, now what will you see is that only one of them will be donating, right? The other donation site is not utilized at all, right? So these kind of ligands are what are called as flexidentate ligands. Like even though we have more denticity sites, right, but not all of them are used, only some of them are used. And it is not necessarily only one can be used. I can have more than this also can be, both the same things can also be used, right? Say I can write it like this. N CH2 CH2, again one more N, right? So we have a donation site here. We have another donation set coming from here. Obviously, H2 is there. No, don't worry about it. Right? So it can act as a monodentate ligand. It can act as a didentate ligand also. Right? So these kind of things are what are called as flexidentate ligands. I hope that makes sense to you. Right? Okay. Now there is another kind of ligands only based on this, denticity only. Right? You have something called as ambidentate ligands. Right, you have something called as ambidentate ligands. Okay, now what do you like? You might have seen this in I think that haloalkanes, haloarenes. You might have seen something like this: ambident nucleophiles. Do you remember?
Like KCN, sir.
Yeah,
2 sites will be there, but at a time only one will interact.
Okay, come again. What is it?
2 sites will be there, but only one site will interact.
Okay, fine. So can I call them as flexidentate ligands then? I have 2 sites, but only one of them is getting utilized. So I can call them as flexidentate, right? Why am I calling this ambidentate then? That's a good question, right? What you're telling is okay, fine. I understand what you're trying to say. But say you are telling that there are 2 sites, or say there are more than one site, right? But out of them only one is used. That means that I can call it as a flexidentate ligand. Why are we calling it as ambidentate ligands then? Ambidentate, ambident nucleophiles. Say whatever ambident nucleophiles you can have, those can be ambidentate ligands also in coordination compounds.
I have a doubt.
Yeah, go on.
If you're saying flexidentate ligand, both the compounds it can donate would be the same, right, sir? In flexidentate.
Both, I don't understand what you're asking.
Like in this, could you move to the left side?
Yeah.
Example.
Mm.
Here NH2 and NH2 are the compounds we donate with.
Okay.
So in Flexi-Dentate ligand, it's always the same compound, right, sir?
No. You're telling the same atom, right? Nitrogen.
Yes, nitrogen.
No, not
So I
necessarily.
think in Flexidentate, they can be polydentates too, right? But in the case of an ambidentate, it will be a monodentate, right?
That's a good observation. Okay, coming to that. So Rohan, answering your question, it need not be always the same atom. For example, you have something called as glycinate. That's a ligand. Okay, so glycinate, if you check, you have glycine structure. This glycine is an amino acid, if you can remember, right? Glycine is an amino acid which is having a structure of, say, this NH2, CH2, COOH. This is what this was a glycine. Glycinate will look like this: NH, okay, NH2, CH2, COO minus. That is what is glycinate. Right now, you have lone pair here and you have negative charge here. It is not necessary that both of them has to donate. Right? Either one can be donate. But in this case, what I see, one side is the oxygen atom, other side is nitrogen atom. So it need not be same atom per se in donating the sites. Yes, are you able to understand? Right?
Yes.
Okay. Yeah, and was it Nanda who was talking about diamide ligands? Was it Nanda Kishore? I don't know who was talking about it. Who was it?
Me, sir. Nikhilesh.
Nikhilesh. Okay, Nikhilesh. Yes, what you're telling is absolutely right. Right. So ambidentate ligands are always going to be monodentate ligands only. Right? They are going to be not ambidentate nucleophiles. I'm so sorry. Ambidentate ligands are obviously going to be only monodentate ligands. Right? But still, they will have two donor sites. Okay. Now, more than one donor site in general. Okay. Right. So more than one donor site means it's not. It's like at a time. Like even though we have more than one donor site, right? At a time, that particular molecule will be able to donate only from one of its atoms. Okay, will be able to donate only from one of its atoms. Like I think, for example, say NO plus or NO minus can be a ligand, right? Nitrogen is having a lone pair, oxygen is having a lone pair. It will never be a case that okay, this side and this side, this will never ever happen. Okay, so even though we have nitrogen atom having a lone pair and say oxygen atom having a lone pair, at that time only one of them will be able to donate, either nitrogen or oxygen. Both of them at that time will not be able to donate like this. Okay, either you can have say NO oxygen to be donated in the metal, right? Or you can have NO nitrogen to be donated in the metal. This only are the possibilities. You cannot have both of them donating from the, both of them donating at the same time. That is not possible. We have a lone pair, but either of them, either nitrogen or oxygen only will be able to donate. Okay, right? These kind of ligands are what are called as ambidentate ligands. Another example is there, CN minus, right? Say CN minus, I know nitrogen is having a lone pair, carbon is also having a lone pair, but again, at a time, either of them, either carbon or nitrogen only will be able to donate, right? Say you can have nitrogen to be donating, or you can have say CN minus, carbon to be donating like this, right? So again, these kind of nucleophiles, these kind of ligands are what are called as ambidentate ligands, right? So they have two donor sites, right? But at a time, they'll be able to donate only from one site. That is why we are calling them as monodentate, not flexidentate, because they have only one site for donation available at a time, right? But two different monodentate sites are possible. Yes, that is okay. Okay, I hope that makes a lot of sense, right? So that is about your monodentate ligands. And there's another type of ligands also. These are what are called as chelating ligands. Yes, any doubts? Devesh, I think you have to mute yourself. Okay. Oh, I have the option of muting. Wow, this looks good. Right. Fine. So I muted him. Right. So another class of, what is the time? Right. So another class of ligand what we have is called as chelating ligands. Okay. Now chelating ligands are actually going to be at least they have what to say, denticity at least to be greater than 1. Okay, denticity should be greater than 1 for chelating ligands. Okay, now what do you mean by chelation or chelation? Like however you want to pronounce it. I think it's pronounced as chelation, like the H is silent. Okay, it's called chelation. Okay, right. So chelation is the process by which I'm going to go for ring formation. Right, chelation is the process by which we can go for ring formation. How? Say for example, there is a metal, right, and say I'm going for ethylene diamine, right, En. Okay, ethylene diamine we can have, right. Say ethylene diamine, what will happen? Say we have one nitrogen, we have another carbon, and another nitrogen atom is there, obviously H2 and H2. Right, now we have a lone pair here, we have a lone pair here, and that is going to get donated. Now what are you seeing here? This part is actually forming a ring, right? How many membered ring? 1, 2, 3, 4, 5 membered ring it is forming. This kind of process, this kind of process is what is called as chelation. Whenever a bidentate ligand or a tridentate ligand, whatever be the thing, right, it is able to form a ring, right? That particular ligand is what is called as chelating ligand, and the process of ring formation is what is called as your chelation. Okay, you understand that there's a ring formation here, easy, right? So those kind of, that particular process is what is called as chelation, and the ligand capable of doing this is what is called as a chelating ligand. Okay, and one important point is that whenever chelation happens, right, whenever chelation happens, that is going to bring in very high stability. Okay, that is going to bring in very high stability. That is all you have to understand. Okay, how stability is obtained, it is really beyond the scope of your 12th class. Okay, don't worry about it, but all that you have to understand is whenever chelation happens, right, that whenever ring formation happens, right, that is going to bring in very, very high stability for the coordination compound or coordination complex, say, right? Okay, so these are all the different types of classifications of ligands we can have. Basically, ligands are the ones who are going to donate electron to the metal atom. As simple as that. Like we can have based on the charge, based on your denticities, flexidentate, ambidentate, chelating ligands, all other different types of ligands you can have. Right? Okay, I hope, is there any questions? If you can, if at all you want to ask, you can ask. Right? Fine. Now moving on. So there are other aspects of this coordination sphere also. Okay. Ligand is done. Okay. Now there are other aspects of the coordination sphere, right? We talked about the metal atom, right? But for the metal atom, there are going to be certain specifications you have to understand. Okay. So when we talk about let me write properly, central metal ion or atom, right? Central metal atom or ion. Right, now we have to know certain things about your central metal atom or ion. Okay, right, we like generally they will be D and F block elements, right? Generally they will be D and F block elements only, right? But not in all the cases, right? Sometimes you can even have S block elements forming a central metal atom that is forming coordination complexes, but most of the cases I can write mostly, right? Mostly they will be D and F block elements. Okay, right. Why is it like this? See, what are the conditions? What are the conditions for a central or metal ion or metal atom to show or say to be a central metal atom in a coordination complex? Or put in a better way, only certain metals will be able to form coordination complexes. Certain metals will not be able to form coordination complexes. Right, now what is the reason? If you check, right, so the criteria for a metal to act as central metal atom in a coordination compound is it should have a small size. Right, why it should have a small size? Because I can have so many ligands and all coming, and it is able to donate electron to this. So if at all I'm able to surround the metal atom, should be able to be surrounded by the ligands. And obviously this will happen if at all I have a big metal atom like this, the ligand surrounding will be very difficult. But if at all I have a small atom, small metal like this, obviously that is more efficient in donation. Is it not? Right? Okay. So they should have relatively very small size. Right? That is the first criteria. Second criteria is that they should be able to show multiple oxidation states. Multiple oxidation states. oxidation states. Right, this is not a very important criteria, but still, right? Say some metal will be able to form +3 also, +5 also, and that is the reason why we say D and F block elements are the ones that are mostly favorable, because they can show multiple oxidation states. Right, we'll study about them maybe in coordination, I mean in D and F block elements separately, right? But these D and F block elements are actually going to have ability to show multiple oxidation states. Okay, so these two are the general criteria. Okay, they will have small size, right? Not bigger atoms or bigger elements, bigger metals will not be able to involve in the coordination compounds, but smaller elements like say lithium is capable, right? Say for example, if I go down the group, lithium, sodium, potassium, rubidium, cesium, I take, right? And they can ask you in this down the group, like say arrange these metals in the order of their ability to form coordination compounds. Obviously ability decreases, right? Ability decreases to form a coordination compound, because lithium is the smallest one, it can form coordination compound, but sodium, potassium, rubidium, cesium, none of them will be able to form coordination complexes. Only the lithium is capable, right? Same way, even in the case of beryllium, magnesium, calcium, strontium, barium, right? You understand that only beryllium and magnesium are able to form coordination complexes. These three will not be able to form, right? Actually, I can give you one good information. This magnesium, right? This magnesium is going to form a coordination complex, and it is actually formed with chlorophyll. What is chlorophyll, people? Chlorophyll. Where have you seen this chlorophyll?
Biology in plants.
What is it?
Biology in plants leaf.
Obviously in biology. Where?
Photosynthesis, sir.
Okay, photosynthesis. Okay, in photosynthesis, where is it? Where exactly?
Sir, plant leaf.
Plants?
Leaf.
Plant leaf. Okay, fine. In plant leaf, what is chlorophyll?
Green pigment.
Thank you so much. That's the exact word I need. It's the green pigment. Right? People, we know that leaves or say generally plants look green in color. It is because of this pigment called chlorophyll. Okay, and these green pigments, that is chlorophyll, is actually made out. Actually, I can show you, right? That's very interesting stuff. Like, let me show you. Google. Chlorophyll structure. Right. Look at this. Right. This is what is the chlorophyll structure. All you have to understand this in the central metal atom here is going to be magnesium. Right. So yeah, don't worry about the complex structure and all. All that I wanted to show is that this is going to be magnesium. Right. The central metal atom is going to be magnesium. Right. This is what is chlorophyll. Okay. Right. So, right. So the criteria you understand, right? We should have small size, and the second one is not going to be that important, but still small size is very, very important, right? Only smaller metals will be able to form coordination complexes. Okay. Right. Now, this we understood, right? So what next you have to understand is how do we calculate the oxidation number, right? How do we calculate the oxidation number of the central metal? CM is not chief minister, it is central metal. Okay, right. So how do we do that? Right, it's very simple. Normally, how you calculate it, right? That's the exact same way we will do. See, maybe I can take some examples. Just give me one moment. Where are you? Okay. Yeah. Say I take, say, we'll take some proper examples. Say I take K3, right? K3, Fe, C2O4, 3, and thrice, like this. Okay. Now, people, you have to understand the different types of ligands. Actually, if I can, there is a table which I can give you. 1 second, just a moment. Yeah, this table, let me give you first. I will, but how do we post it here? Maybe from internet, and we will get 1 second. Okay, I think this should be good, right? The next one also I can take, right? Okay, this is good. Where should I post? Okay, let me post it here. Okay, and another one also coming. Okay, so let me make this little big. Okay. Okay, so this I think you can know, right? So this table, right? I think in your book also some kind of things will be there. Okay, so different kinds of ligands, different kinds of their unidentate, bidentate, all these stuff, tridentate, positive, negative, all those things are there, right? Fine. Again, okay, and the names of the ligands are also there. Okay, but I think something is getting let me do it this side. Okay, better, right? So you can just look into this, right? Cyanide, like cyanide ion, Cn minus, thiocyanate, SCN minus, isothiocyanate. We'll come back to this later. Okay, don't worry about this, right? All I have to understand is these are the different kinds of ligands, and not all of them are going to be important to you. Okay, not all of them are going to be important to you. Whatever is generally used, we'll try to understand. Okay, right. So fine, that is okay. Right, next. So this C2O4 is what? C2O4 is nothing but COO minus COO minus. Okay, this C2O4 is nothing but COO minus COO minus, and this is nothing but your oxalate ligand. Right? We know oxalic acid is what? Oxalic acid is COOH, COOH. That is what is oxalic acid. If I just remove the H plus and H plus, you're going to end up with COO minus, COO minus. Right? We have to know the charge. It is nothing but C2O4 2 minus. That is how we represent this. Okay, right. Anyways, we are trying to calculate what is the oxidation number of the central metal atom. That means here the central metal atom is Fe, not potassium. Please understand, this is your counter ion, and this is your counter ion. Okay, right. So whenever some counter ion is given to you, right, and you want to find the oxidation number, it is better to remove the counter ion and write the coordination pair alone. Right, now we understand that it is K plus, right? And when I have 3 Ks, that means I'm going to have 3 numbers of K plus ions. Is it not? Now this molecule is whole neutral. So how would I have been able to ionize this? I would have been able to ionize this as 3K plus Fe C2O4 thrice. And what should have been charge on the coordination sphere? Obviously, this is total plus 3. So this should have been minus 3. Okay, this should have been minus 3. This is the first step you will do, right? If at all the coordination sphere only is given to you, well and good, superb, right? But if not, we have to first make the coordination sphere. Okay, right. Then what you have to do, like normally how you do, then you do, right? So for Fe, let us keep it as X. Okay, for Fe, let us keep it as X, right? And we understand for each of the oxalate, it is going to be minus 2 charge, right? For each of the oxalate, it is going to be minus 2 charge. And here we have 3, right? So I can write 3 oxalate ions are there. And each of the oxalate ion is going to have a charge of minus 2. Right, and that should be equated to the overall charge of the coordination sphere. Like this and this, if I add, right, you should be able to get the overall coordination sphere's charge, that is nothing but minus 3. Okay, right. So now I can easily do this, right? So X, you will be able to find it as it is going to be in plus 3. So Fe is actually in its plus 3 oxidation state. That is how we calculate. We'll take more examples. Okay, say I have we have PT NH3 4 times Cl2, right, and we have Cl2 outside. Okay, now I want to find what is that oxidation number of platinum. PT is platinum. Is it not? Right. So now what you understand is we have to remember what are all the neutral ligands, what are all negatively charged ligands, and what are all your positively charged ligands. We know that ammonia is a neutral ligand. We have to know this. Again, H2O is a neutral ligand, right? Like there are only few neutral ligands, we have to remember them. Okay, and obviously Cl is nothing but Cl minus. All right. Okay, right. Now again, what is the first step? First step is that you have to remove the counter ion and write only the coordination sphere, right? You have to remove the counter ion and write only the coordination sphere. And we understand that it is again going to be Cl minus only, right? And we have 2 such Cl minus, right? So if I go for ionizing this, we will be able to write it as PT NH3 4 times Cl2, right? We'll talk about the charge here. Obviously, you're going to get 2 Cl minus ions outside. So totally here I have minus 2. So obviously the counter should be positive. So it should be plus 2 on the coordination sphere, right? Okay. Now, obviously now we'll be able to calculate the oxidation number of platinum. So let us keep the platinum as X, right? For ammonia, it is 0. There is 0 charge on ammonia. Right, and we have 2 chlorine atoms, each of them having minus 1 charge, and that total is equal to plus 2. Right, so what will you find now? You will find that your X, this is going to be minus 2, and that is going to go this side. I think it is going to become plus 2, so that is going to become plus 4. Right, so the platinum is going to be in plus 4 oxidation state. Okay, right, you have to be very, very careful with this. Right, so maybe let us look into the different types. Like say you already know most of them, right? All right, so we have Cn minus, you know that, halide, I minus, hydride, H minus, nitride, nitro, NO2 minus, Again, these two are again ambidentate ligands. NO2 minus, that is nitrogen is going to act as the donor side, and nitrite ion, that is in this case ONO minus, that is in this case oxygen is going to have going to act as a this thing, right? Again, they are ambidentate ligands example, right? Nitrate, hydroxide, amide is okay. Again, these two, SCN minus and NCS minus, again are going to be what is that? Example for ambidentate ligands. Same formula, right? Either sulfur can donate or nitrogen can donate. Okay, either sulfur or nitrogen can donate. Acetate we know, the oxide, these are all are okay, normal stuff. Okay, look at this, didentate, oxalate, which we spoke about, right? And any other important thing which you have to know, glycinate, we spoke about this, glycinate, right? This and all is not important. Then this and all you don't remember, nothing, don't worry about this, right? Any other important, yeah, ADTA, we spoke about this, right? ADTA is a structure, right? And then we have ammonia, neutral ligands. Look at this, ammonia, H2O, NO can be, see, NO can be positive, can be neutral. I can have a negative charge also. Okay, right? But don't worry, mostly you will see only NO plus as the this thing. Mostly you will see only NO plus. Okay, carbon monoxide we saw, this one are not important. pH3 is little important. Okay, if you want you can remember. And then ethylene diamine we saw, right? Okay, then tridentate and all, that thing not much important, don't worry. Yeah, these are all things, normal things which you have to remember, right? Whatever we have seen, those are all the things which you have to remember. Other things, all the other things which are there in the table are not that important. Okay, right? And if you look at this, we are going to use, like, the name which we use here and the name which is given here are little different, right? You can see that, isn't it? Say here it is cyanide, here we write cyano, here we write halide, here we write halido, right? Here we write nitro, here we write, again here nitro, here is same, again look at this hydroxide, here we write hydroxo, we write aqua. Oh no, I'm talking about H2O. Where is H2O? H2O I know is water, but look at the name which you are going to use, aqua, right? Ammonia, if I have, I'm going to use it as amine, right? So these are all the names which you have to remember for going for IUPAC name, right? But that we'll see in a few minutes. Okay, that we're going to see in a few minutes. But for that, the ligand's name, that is the normal name, how you call it, and what is the IUPAC name which is going to be used in your IUPAC naming of the compound is going to be different. Okay, and those names we have to remember. Okay, now another example is say oxalate, you are going to use it as oxalate. Mostly you will be replacing E with O. Oxalate, oxalato, cyanide, cyanido, right? Something like that we'll be using. We'll be replacing E with O, chloride, chlorido, right? Mostly we'll be doing this, but only for your neutral ligand, that is your ammonia and your H2O. Those two alone you have to remember the name, amine and aqua. Right? This you have to be very careful. Okay, right? Other than that, you will not have anything. See, hydroxide, hydroxido, amido, amide, amido, thiocyanide, thiocyanate, thiocyaneto, right? Isothiocyanate, isothiocyaneto. Again, the only thing which you are doing is whenever we have a E, we replace with O. That is the only thing which you are doing. Other than that, there's nothing much different to this. Huh? It's gonna get over. One second, guys. My charge is gonna get over. Right? Okay. So these are the different names which you have to understand. The names of the ligands. Okay. Right. And we understood now how to find the oxidation number of the ion also. Not ion, the central metal atom or the ion. Right. Now, one more thing I ask you. Say, for example, if I have NiCO 4 times. Right? Can you tell me what is the coordination number here? Oh, sorry, not coordination number. Sorry, the oxidation number. Can you tell me what is the oxidation number of nickel here? What is it? This is carbon monoxide. Okay, and we have nickel, and this is the entire coordination sphere. what is the coordination number? Sorry, again, I'm telling, what is the oxidation number of nickel here? What is the oxidation number?
Yes, sir.
What? Okay,
So
overall.
CO minus, right, sir?
Sir,
No, it's why you see on the
for
minus.
CO
Carbon
it's zero, so
monoxide.
is it
Yeah,
zero,
it is
sir?
zero. Yes. Right. Carbon monoxide is a neutral ligand. Right. So we have X plus 0 into 4, and overall the charge is also 0. So nickel is in 0 oxidation state. Okay. Nickel is in 0 oxidation state. You have to be very careful with this. Okay, well, that's why I told you what are the neutral ligands, what are the negative charge ligands, what are the positive charge ligands. We have to remember. If you don't remember, you will not be able to calculate the oxidation state of the metal. Right? So you can even ask, 0 oxidation state is possible? Yes, 0 oxidation state is also possible. Right? We will try to understand the bonding in detail. Okay, how the bonding is, like how exactly the coordination bonds are formed, what is the shape, what is the geometry, what is the all these things, not bond angles. But yeah, what are the shapes and geometries also we will see, but not now. Okay, but for now, what you have to understand is 0 oxidation state is also possible. No doubt about it. Okay, right. What is the time? We have time. Okay, so now I think I can introduce you to your this thing, right? IUPAC naming. Okay, before that, maybe we'll talk about one more thing, right? We talked about the oxidation number of the central metal atom or ion, right? We can also speak about the coordination number. Right, coordination number of the central metal atom or ion. Okay, right. Now, what is the coordination number? Right now, how do I properly define this? Right, coordination number of central metal ion is nothing but the number of monodentate ligands surrounding your central metal atom. Surrounding the metal. Okay, number of monodentate ligands, very important. Number of monodentate ligands surrounding your central metal atom or ion is what is called as your coordination number. Okay, say for example, if I write some cobalt En thrice, say 2 plus, something like this. Now again, you have to understand what do you mean by this En. Now people, again, these are some representations. Where are you? Did they give it here?
Yes, ethylene diamine.
Yeah, ethylene diamine.
It's there
But
below bidentate, sir. We're reading bidentate.
yeah, ethylene diamine. Okay, this didentate will be there. Bidentate ethylene diamine, but they have not given any symbol. Okay, it's given. Right, look at this, people. Right, the symbol for ethylene diamine use this En. Okay, we will not write the full formula like this in your coordination complexes. Ethylene diamine, if it is there, we will just write it as En. That is understood. Same way for dipyridyl, Pi, and again same way for what is it? Okay, they don't have EDTA given. Okay, hexadentate EDTA. How do we represent? Look at this. EDTA 4 minus. That is how we represent. Okay, because all these formulas are very big, right? So we will not be able to represent them in the coordination sphere. So rather we'll be using their shortcuts or symbols for these big molecules. Okay, so when I say En is nothing but ethylene diamine. That is NH2, CH2, CH2, NH2. Okay, right. Now what I'm telling here, I want to find what is the coordination first. Tell me. Okay, before we move on to this, can you tell me what is the oxidation number of cobalt here first? What is the oxidation number of cobalt?
It's 2 plus, right?
2 plus, sir.
Yes, plus 2, right? So we can write X. Obviously, this is going to be a neutral ligand, so 0, and the overall charge is plus 2. So obviously, this is going to be in plus 2 oxidation state. Very simple. Okay, right. Anyways, now we'll calculate the coordination number. Now, what did I tell you? Coordination number is nothing but the number of monodentate ligands surrounding the metal. Right now, in this case, what we have taken a didentate ligand, right? That means, can I tell here I have 3 didentate means, can I tell it as 6 monodentate ligands? Is it not? When I, what do you mean didentate? That means 2 monodentate ligands, something like that, right? Two donor sites are there. Is it not? Right? So basically how we have to define it is number of monodentate ligands surrounding the metal. In this case, didentate ligand is there. That means one didentate can be considered as 2 monodentate ligands. Is it not? So if at all I have 3 didentate ligands, here I have I can say that I am going to have 6 monodentate ligand. So I can tell the coordination number here is 6. How many ever monodentate ligands you have, that much is the coordination number also. Okay, say let me give you another case. Say I have okay, say I'm getting good examples. Wait, I'll give you a good example. Okay, anyways, I'm not getting it. I'll only give you. Say if I write CrCl3H2O thrice. Okay, that is the compound we have. Okay, now can you tell me first what is the oxidation number, oxidation state of chromium here first? Tell me.
-3, right?
Are you sure?
Sorry, it'll be +3.
+3 is correct, right? How? X -3 for chlorine, H2O is a neutral ligand, so 0 for that, right? And the overall charge here is 0, so X should be equal to +3. Okay, oxidation state is +3, that's fine. What is the coordination number?
6, right?
6, right? This is monodentate, this is also monodentate, so no problem. 3 + 3, right? 3 + 3 is going to become 6. That is your coordination number. Number of monodentate ligands surrounding the metal is what is your coordination number. Very simple. Okay, right? So I think we will stop with this for today, people. Right? We'll stop this for today. Next class, we'll be starting with your, what is that? IUPAC naming. Okay, right? So we saw all the basic stuff today, right? So we will be starting with IUPAC naming and then we'll move on to isomerism. What are the different types of, this kind of compounds can also show isomerism just like your organic compounds. Okay, so we'll see isomerism and then we'll move on to the bonding, how exactly the bonding is happening, the shapes, geometries, everything we'll try to see. Okay, right? Any questions anybody has? Okay, right. Thank you so much, people. We'll meet again, I think next week.
Thank you.
Thank you, sir.
Thank you.